Hello. So today we're going to discuss some use of Mercer kernels and the theory of, the Mercer theorem in order to derive some convergence rates, so to study theoretically the performance of kernel-rich regression when we do regression with the Mercer kernels. So maybe to start this section, let me come back 3 slides in the past to the visual summary of what Mercer theorem told us. So basically, it told us that if you have a Mercer kernel, meaning if you start from a space X with a measure nu, and here the measure is kind of illustrated with this pinkish or reddish ellipsoid. So assume this is a distribution mu. Then from this nu, we can define an operator. Remember, this was an operator from L2 of nu to itself called Lk, which had eigenfunctions and eigenvalues, so psi and lambdas, which are represented in green here. So of course, it's a picture, where we put on the same image the space X and the function. So maybe to understand the meaning of this image, you can think of psi probably like linear functions, and so it's represented by the vector such that the function psi1 or psi2 obtained by taking the inner product of the point in the red zone with the blue vector psi1 or psi2. Right, so anyway, the important thing is that from the nu, we have just the operator creates psi1 and psi2, and we have seen that, so by construction, the L2 norm of psi1 and psi2 are equal to 1, because these are eigenfunctions of the operator in L2. You can think and notice that, on this picture, psi is small in the direction where nu is large. And so the important thing that we have seen is that when you start from psi1 and psi2, if you rescale them, meaning if you multiply psi1 by square root of lambda 1 and psi2 by square root of lambda 2, and the same for higher order eigenfunctions, then you get new functions, which we call phi1 and phi2. And we have seen that these functions, in fact, form a basis of the RKHS, right? And so this is in green here. So the phi's are just rescaled versions of the psi's, and they have norm equal to 1, and they're orthogonal to each other in the RKHS. So in a sense, Mercer theorem, you can think of it as a way to describe the RKHS. We use the word, I think, ellipsoid. So it's an ellipsoid in L2. But here, something that we will use is that it's possible to move from L2 of nu to H through this transformation, basically that rescales according to each direction of the eigenfunction. Right, so a bit more formally, what we have seen, and this is recapped here, is that in fact there's an isomorphism, meaning this isomorphism is this linear transform, which is a bijection and preserves the distances between the RKHS H and the L2 norm, L2 of nu. And remember that L2 depends on the nu, meaning that if you choose another nu, you would have some different psi's, different lambdas, but you will always have this isomorphism. So mathematically, this isomorphism, if we start from L2, if you take, in the plot, we said, look at psi1 and psi2, then psi1 is transformed into phi1 by multiplication by square root of lambda 1, the same for psi2. And more generally, if you have any function in L2, if you decompose it over the psi basis, meaning if you write your function f as a sum of ai psi I, then the transformation corresponds to scaling each coordinate by multiplication by square root of lambda I. And so the main result is that the norm of the function f in L2, so the norm of the sum of ai psi I in L2, is equal to the norm in the RKHS H of the transformed function, meaning of the sum of ai square root of lambda I psi I, right? So notice that this multiplication by square root of lambda I is not exactly the same as the operator L, because remember that the operator Lk had the property that psi is an eigenfunction with eigenvalue lambda I. So if instead of the square root, we would have just lambda I here, this would be exactly the operator Lk. But here, to get this isomorphism, we need to multiply by the square root of lambda I. So we call this operator the square root of operator of lambda of Lk, and we write it Lk to the power 1/2, right? It's just because of the square root in lambda k. Okay, so this is cute, and something that we will use now is the fact that this isomorphism allows you, sometimes it's like a technical tool that you can use if you want to make proofs, that allows you when you have, for example, when you need to estimate L2 norm, if at some point you have, in some computation, L2 norm of a function, then you can rewrite it as some RKHS norm of the modified function. So when you modify the function by the operator LK1/2. Okay, and so we'll see how this can be useful now, just for example, to derive some statistical bounds, because sometimes it's easier to estimate or to compute RKHS norms than L2 norms. And it could be the converse. Sometimes you may want to compute some RKHS norm. Then it's useful to say that because it's an isomorphism, you can invert it and you can rewrite any RKHS norm, in the case of Mercer kernels, as some L2 norm of some modified function, right? So this is, if you do mathematics, if you want to study the mathematics of machine learning, I would say this is a very useful and common trick when we study learning theory. All right, so to illustrate the trick, we will focus on a kind of simplified version, I will explain why, of studying what, whether kernel-rich regression is a good method or not. So just a recap, kernel-rich regression is a method that performs regression. So given some points, x1, xn in some space, capital X endowed with a kernel, and we would assume that here we have a Mercer kernel, and given some values y1 to yn, kernel-rich regressions try to estimate a function f in order to, to fit y as f of x. And so we have seen that to do that, kernel-rich regression solves an optimization problem in the RKHS by minimizing a sum of two terms. The first term is the mean squared error, a standard thing, and the second is lambda times the L2 norm of f, lambda times the square norm of f in the RKHS. If you come back to the course that we have seen in the supervised method, then you will notice, that we can solve that explicitly, and we know the solution. The solution is f hat lambda as the sum for I equal 1 to m of alpha I k of xi x, where alpha is a vector. So the vector of alphas is given by this formula, is the inverse of k plus lambda n identity multiplied by 1. Right, so this is what we have seen before. It's an algorithm that you maybe have implemented. Now, the question we address now is it good, right? We estimate f hat of lambda. Can we say whether it's a good idea to solve that? What can we say about that? So to answer the question of is f hat lambda a good function or not, we need to make a model, right? To say what is a good function, how do we relate a good function to the fact that we observe data, etc. And this is where typically we do a statistical model. So here the model we will make is that we assume that x and y's are related probabilistically by a distribution p. Right, this is the thing, and the important thing that we'll make a couple of assumptions here. I jump to the second point directly. The first thing we would assume is that x has to come from somewhere, so we will assume that x follows a distribution nu. And it's not an error here. The nu that we will, which is a distribution of the x, will be the nu that we use to define the Mercer kernel. Remember that the Mercer kernel has to be a continuous function over a compact space, and we had the distribution nu over the compact space. So here the nu will be the distribution of the random variable that we observe, right? The second assumption we make is that once we know how x is distributed, we need to decide how y is distributed. And so here, for today, we will assume that f is in fact a function of x, which is f star of x, where f star is in the RKHS. So this is a second big assumption. We assume that we have a kernel that describes a set of functions, and that the true regression function is in the RKHS. And we assume that, in fact, we don't observe exactly f star of x, but that there is some noise independent, which we call epsilon, which, for simplification, will be assumed just to be a normal noise, so a noise sampled according to a Gaussian distribution with variance sigma square, right? So it's like the simplest and most standard model in statistics when you study regression. So this is the model, and so now we need to explain how it relates to what we do. So it relates through the assumption that the data we observe, so the xi, yi pairs, we assume are random variables, and they are sampled IID, so independently and identically distributed according to P. Right, so now this gives us our model. We assume that we have the distribution nu, the function f star that we don't know. We observe the xi, yi pairs, and from them we infer a function f hat of lambda using kernel-rich regression. And the question is that a good function? And so to quantify if it's a good function, we will use a standard method, which is to define its mean squared error, which is simply the expectation over future realizations, so over new random variables y, x, y, meaning not the ones we have observed, but that typically could be the one we will observe at test time. So we will take the expectation according to the sampling of y and x of the difference between y and f hat lambda of x, right? So how good we are in predicting y from f hat lambda of x. This is our goal. We want this to be small. And the question is it small or not? Okay, so of course, so here, I mean, maybe in this notation, I should say that we hide something in the expectation. So I said here we take the expectation in x and y, but of course, f hat lambda itself is a random function because it depends on the points we see, and the points we see themselves are IID realization of the xy pair. So as we will describe, I mean, we quantify the mean squared error of the estimator itself, which is not a particular realization of f hat lambda, but more of the algorithm. And we will call MSE of f hat lambda the expectation of the mean squared error of f hat lambda, taking the expectation over the realization of f hat lambda itself. Right. So this means that in the expectation, we have expectation with respect to the xy pairs that would be test points, as well as the expectation over the training set, which creates a random f hat lambda. And so we want this to be small. All right, and so to do that, we will use the property of Mercer kernels, which tells us that if so nu is a distribution of x, and so from this nu we have an operator, and we have an eigen set of eigenfunctions psi I, and corresponding eigenvalues lambda I. And so remember that by this isomorphism, once we have the psi I, we also have an eigenfunction, an orthogonal basis of the RKHS given by phi I, which is the square root of lambda I psi I. Okay, so the rest of the discussion today will be about trying to compute, to upper bound, to estimate this MSE term, and try to assess if it's small or not. Hopefully it will. And this will allow us to say that doing kernel-rich regression is good because it's asymptotic, or maybe not asymptotic, means whatever is small. And so we will try to go a bit to some technical details. So I will not go through all the equations today. I will just highlight the important steps and try to show you how we use this isomorphism between L2 and H to derive some upper bound on MSE. All right, so the first step in the analysis is to simplify a bit MSE. So MSE is the global error, right? It's on average how bad we are. And the first step is, I would say, classical. If you have ever studied, for example, how the mean squared error of ordinary least squares or ridge regression are, is to decompose the MSE as a sum of three terms, which is written here in red. So we write the MSE of f hat lambda as the MSE of f star. So this is just the noise due to the epsilon, in the sense that even if we knew exactly f star, then we would never be able to predict exactly y from x, because there is a difference, y is f star of x plus epsilon. So there is some inherent noise in the data that is like a lower bound on the MSE we can get, even if we knew f star. Now, so this is not a very interesting term, But once you remove the effect of the epsilon, meaning the effect that you, even if you knew f star, you would not be perfect, then there remains a question that you don't know f star, you want to estimate f star, and you estimate it with f hat lambda. And so there is always a discrepancy between both of them. And so the discrepancy in terms of MSE translates into a sum of two terms, which I write here as b lambda and v lambda. And the choice of b and v is just because they are called the bias and the variance. So the equations themselves are a bit long and ugly, but this is just because we rewrite standard bias and variance terms with the notations that we have used so far. But I will go through, the derivations of how we get them. But just if you have ever studied, an estimator in terms of bias and variance, this is exactly what we do here. So in particular, what is the bias? The bias, there is some bias here because, if we come back to what kernel-rich regression does, you see that if we had many, many points, like n very large, then in theory, we should not need to regularize, like to minimize the mean squared error plus lambda something, which would just minimize the mean squared error to recover f star. However, we don't do that. Here, we decide to minimize the mean squared error plus some penalty, the regularization. And so because of this penalty, we would, if n tends to infinity, and for example, lambda does not tend to infinity, then we would be biased. We would not estimate f star, but we would estimate f star, move towards smaller norms in RKHS. So this is the bias, basically. The bias is that on expectation, we don't expect to recover f star by minimizing the mean squared error plus a penalty. And so in particular, you see that if we look just quickly on try to understand what's the role played by lambda in b lambda, we see that, for example, if lambda gets very small, so if we don't regularize much, then in the equation of b lambda, suppose, for example, that lambda is equal to 0, then the equation, the term lambda n identity disappears. And so, assuming that there is some matrix which is invertible, we have the matrix phi n transpose phi n inverse times itself. So the big term here becomes identity. And then we have identity minus identity, which is 0, right? So when lambda is equal to 0, b lambda is equal to 0. So there is no bias when we don't regularize. And when we increase lambda, so when we start regularizing, then we create some bias. And it translates into a term in the MSE. Now, the variance is a bit the opposite. The variance is, how much you stabilize your prediction. Like if you see different training sets, you will estimate different f lambdas. And if lambda is very large, for example, then there will not be much difference in the f lambdas. But if you don't regularize much, there is a risk that the f lambdas may fluctuate a lot. So this is captured by the variance terms. And in particular, if we similarly look at the effect of lambda, you see that when lambda gets very large, so when you regularize a lot, then in the v lambda terms, you have lambda, so you have the term lambda n identity that gets very large. So this matrix becomes very, diagonal with a strong term on the diagonal. And because you take the inverse of that matrix, overall, it will make this big term, we will talk about it later, very small because you divide by lambda. And so the variance gets small. Right, so we recover standard notions of bias and variance, and in particular, there is a trade-off between b and v when you move lambda. For small lambda, you don't regularize much, so you have a small bias but potentially a large variance. And for large lambdas, you create some bias, so b lambda increases, but the variance decreases. And so this is like the mathematical translation of finding the trade-off between bias and variance in terms of moving lambda. Okay, so let's start by trying to explain a bit where these equations come from. And again, as said, it's a bit technical, but I will just highlight the important point here, which is to use this isometry between L2 and H. So where does it come from? Well, if we start, if you wanted to prove this theorem, you would start by writing the MSE of f hat lambda as, by definition, the expectation of, the difference between y and f hat lambda. Now, you know that y, the true y is f star of x plus epsilon. So you have, you have epsilon plus the difference between f star of x minus f hat lambda of x. And here the first step is first, I said that there is some inherent noise because of the epsilon. Well, we enter the expectation because you assume that epsilon is independent from x. This was an assumption. Then you can just decompose the expectation of the sum of the square as the sum of the expectation of the squares because the cross term disappears. You assume that the expectation of epsilon is equal to 0. And so you recover the epsilon of sigma the expectation of epsilon square, which is equal to sigma square, and this is the mean squared error of f star, so this is the first term. And then what remains is the expectation of the squared L2 norm of f star minus f hat lambda. Right, so this is the important thing. This is where we should see the bias and variance pop out. Now, in order to upper bound the L2 norm squared of f star minus f hat lambda, this is where we use the trick, which I said is an important trick, to rephrase the L2 norm into an RKHS norm. Right, so here we use this isomorphism between L2 and the RKHS in order to rewrite the squared L2 norm of something, which in this case is f star minus f hat lambda, into an RKHS norm. But of course, we need to multiply this function by the operator Lk to the power 1/2. Right, this is a direct application of the isomorphism I mentioned between L2 and H. And so the reason we do that is that this will allow us to do computations because, roughly speaking, remember that f star is supposed to be in the RKHS, so we will assume it has a finite norm. F hat lambda, remember, was we have the formula, and the formula can be easily expressed in the RKHS, so we should be able to describe what is the coordinates of f hat lambda at the RKHS. And Lk, the operator in the RKHS, is quite simple because on the basis of the phi's, if we write everything in the basis of the phi's, then Lk is simply diagonal because remember that Lk is just a multiplication. So Lk to the power 1/2 is just a multiplication by square root of lambda I when you're along the axis of psi I, and so along the axis of phi I. Right, so technically the fundamental interest of rewriting this L2 norm as an RKHS norm is that we will be able to compute all the terms just by doing classical computation because everything here is easily expressed in the RKHS, and so we can just then compute the L2 norm in the RKHS. All right, so this is the important technical aspect of the proof, which I wanted to highlight. Then once you realize it, the rest is quite standard, I would say. Coming back here, so as I said, the only thing we will do is just compute an L2 norm. And to compute an L2 norm, we will just rewrite all the terms, so f star, f hat lambda, and the operator, into some basis of the RKHS. The basis we take is the basis of the phi i's. So we just need now to explicitly compute, for example, what's the coordinate of Lk to the power 1/2 of f star in that basis. What's the coordinate of Lk to the power 1/2 f hat lambda in that basis, and then make the difference and do the sum of the square to obtain the L2 norm because the squared norm in the RKHS because the phi's are our basis in the RKHS. Okay, so I will skip the details. I think there is no difficulty in doing that. Just if you try to redo that, just notice that what we call E. So here we create a small function E, which goes from the RKHS to small L2. So small L2 is just the set of sequences which are in L2, meaning sequences of numbers such that the sum of the square of the numbers converges, right? And so this mapping here is just mapping of any function in the RKHS to its coordinates onto the basis, right? So it's just a notation to say what's the coordinates of a function f on the basis phi I. And so what we will do is that we will basically compute, in order to compute that, I said we will compute the coordinates of all these terms in this basis. So this means that we will compute E of f star, E of Lk 1/2 f star, E of Lk 1/2 f hat lambda, etc. And this will just allow us then to estimate a big vector, and then we will do the sum of the square. Right, so I think I will just I'll leave it to you to study the next few slides that do that. There is no difficulty. Maybe what I can mention is that something important to notice is that the operator LK in the basis of the phi is diagonal. This is, I said already, because you know that phi I is transformed into lambda phi I. So if you have any function f that decomposes over the basis of the phi's, then so this means that if you call E of f the coordinates of the function f, then the coordinates of LKF are just the coordinates of f multiplied by lambda I. And so you can see that as an operator T, which is diagonal. Right? This is one comment. Second comment is that here, you need to be a bit, there are a few equations to write, but all these equations are meant to try to capture what is the coordinates of f hat lambda. So we know that for f hat lambda, we have a formula in terms of the sum of alpha I k of xi x. So there is just a small game here to rewrite what we know about f hat lambda, and extract its coordinates on the basis phi. And so we get this big thing. This big thing depends on y because the alpha depends on the y's, and so it's almost done. But at this line here, we need then to replace y by f star of x plus some noise. And so we need to define what are the coordinates of f star. We call beta star the coordinates of f star. And so putting all together, replacing y by its expression, we finally get what I said we would get, which are E of f star minus f hat lambda, which are just the coordinates of f star minus f hat lambda in the basis phi 1, phi 2, phi n, so in the RKHS, right? So it's a bit long, but this is where you see appear all these big matrices you just obtain by direct computation of these coordinates. And finally, in order to estimate the mean squared error, we just need to estimate the expectation of LK 1/2 times f star minus f hat lambda squared norm in H. So this thing, we just replace, all the things of f star minus f hat lambda, we replace them by their expression in order to get a sum of two terms. All right, so please just redo the computation by yourself. All right, so this was the first thing. So you notice that in order to move from to decompose the MSE as a bias plus variance, there is no conceptual difficulty, except there is this small trick to rewrite to express a L2 norm as L2 norm over nu as an RKHS norm. And by the way, notice that here we still have L2 norms, but these are small L, so meaning that these things here are big vectors, and by L2 norm we mean the sum of the squared coordinates of these vectors. Okay. All right, so this is the first step. Now, what we need in order to upper bound the mean squared error is to find some upper bound over the bias and the variance as a function of lambda, and maybe optimize lambda, etc. So here we will do something. I will skip a step in the formal proof, which because it's a bit technical and it's not really relevant for us. But the step I will skip is, sorry, I will come back to the expression in B lambda and V lambda. You see, these are expectations. And so these are expectations with respect to two things. One is with respect to the epsilon, which is on the new point x, y. What is the noise epsilon? So how does y differ from f star of x? And you see there is an epsilon here in the variance. And the second expectation is with respect to the training set, so which is hidden here in the matrices phi n, right? So the phi n are random matrices that depend on the training set. So what we will do is that we will not study in detail the effect of this fluctuation, and we will directly replace phi n transpose phi n by its expectation. So what I mean by that is that if you assume, for example, that n is large, then phi n transpose phi n will converge to a matrix, which in fact I write here. phi n, phi transpose, you can show that it converges when n is large to a matrix which is just a diagonal matrix, very simple matrix. Right, so it's not exactly equal to that. It's just a random, so it's a diagonal matrix plus some fluctuation. And in the rest of the proof, we will just assume that phi n, phi transpose is not random, but it's exactly equal to its expectation nt. Right, so to remember that we made this approximation, I will call b tilde lambda and v tilde lambda the bias and variance when we made this assumption. I just want to say that in fact we don't, I mean, we cheat a bit, but it's easy. It's just technical and takes a few more slides to do the correct, to estimate what this approximation costs. So it adds a term in what we will get. If you want to see all the details, there are plenty of papers. For example, here I link a paper by Dicker and al. That does basically the same proof and details how you can justify this approximation. Right, but so for us, we will just assume that phi n, phi transpose is equal to nt, and we will see what it gives in terms of how to choose lambda, etc. Okay, so when we made this approximation, then now we need to upbound b and v as a function of lambda. And so we will do it and get these two upper bounds. So it's still not very clear from there. It's like an intermediary lemma that gives you some, you see, upper bound on B and V. The upper bound on B depends on the norm of F star. The upper bound on V depends on just, some eigenvalues. And so here, I mean, these are upper bounds that are valid for any j, so for any integer, and we will optimize j just like we will optimize lambda. These upper bounds will hold. Okay, so again, there is no technical difficulty, there is no conceptual difficulty in that we will do. I will just explain where it comes from. All the proofs are in the slides, and I will leave it to you to redo the computation if you're interested. Okay, so here is, for example, for the bias. So let me maybe come back to the expression of the bias, right? So the bias is here. So remember here that I said we will assume that phi n transpose phi n is not random anymore, but it's equal to a matrix, which in fact would be nt. Then the expectation disappears. There is nothing random anymore. And so what we need to upbound is just the small L2 norm of this big thing, okay? And so in order to do that, we will just compute it. And in fact, it will be quite easy because once you replace this by t, you notice that t is a diagonal operator. So all these, square root of t times identity minus blah, 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 up to the end of the parentheses will be a big diagonal operator, right? And so this means that if you just assume that beta star has some coordinates, so beta star has coordinate beta star 1, beta star 2, etc., then this big vector is just a diagonal operator times beta star. So you can compute, we will compute just its coordinates. And so to estimate the bias, we just make the sum of the square of the coordinates, which will be the sum over I of the beta star I square multiplied by something that will just be, if we're careful, the diagonal term of this operator, where we will see appear some lambdas. Okay, and basically v lambda will be the same. Okay, so just to check that just to repeat what I said, we first look at the big parentheses and see that the big parentheses, if you're careful, you will notice it's just a diagonal operator. Think of it as a diagonal matrix of infinite size. And the diagonal term is lambda times square root of lambda I over lambda plus lambda I. So what we have is now that we can rewrite the bias term, as a sum for I equal 1 to infinity of these squared diagonal terms times beta I squared. And then to get the upper bound, we do something more, which is that this sum from 1 to infinity, we split it in two to some arbitrary number j, and we provide two different upper bounds depending on whether I is between 1 and j or above j plus 1. So the upper bounds have nothing complicated. You can check them, and we will see, it's just a technical thing in order to upper bound b lambda by optimizing j as a function of the decrease of the lambda that we'll do in the next step. Okay. So the upper bounds, check them. They are based on very simple things, and they give you, one upper bound for I between 1 and j, then another upper bound for I larger than j plus 1. And when you combine the two upper bounds, you get finally the upper bound on on the bias. For the variance, we basically do the same. Here, there is still some expectation because remember that what was random was phi n, so it's not random anymore. Now we fix phi n transpose phi n to be equal to nt. But there is still the epsilon. Epsilon is the noise in the future data. So we have some expectation just with respect to epsilon, and I will not redo all the computation. But we basically again work out this expectation of the square. So we we write the square norm of a vector as the trace, so the sum of diagonal entries of the vector transpose itself. This allows us to move the expectation inside because now we just have epsilon transpose inside. We notice that the expectation of epsilon transpose is sigma square identity. So this removes the expectation. And we end up with sigma square over n times a big sum for I equal 1 to infinity of lambda I squared divided by lambda I plus lambda squared. And just like for the bias, now we split this sum as a sum for 1 to j, and then as a sum for j plus 1 to infinity, where j is just any number. And we provide two different upper bounds on the left and on the right. I skip them. So this is the one on the left. This is the one on the right to finally get an upper bound on v lambda that is sigma square over n multiplied by a sum of two terms that you can adjust by adjusting j. Okay, so once you have all that, I show again what we have proved. We have proved that MSE was bounded by sigma square plus beta lambda plus v lambda. Then I have approximated beta lambda and v lambda by the corresponding tilde. And I said, if we could, with some more effort, we could directly have an upper bound on b lambda and v lambda. And this is the upper bound we get. Now the question is it good or not? It's not completely clear from that. So here now we will try to study these two terms and try to optimally choose the j, the lambdas, in order to see if we can get interesting things. And so the short answer is yes, we can get interesting things. And this is a summary of the final upper bound we can get, depending on the assumption we make on the decrease of the eigenvalues. Right. So something interesting here is that the final. So in statistics, often, at least for this course, we're just looking at things like when n gets very large, how fast does the MSE decrease? This is what's called asymptotic analysis of the learning theory. And we know that depending on the assumptions you make on f, like if the true function is very smooth or not, then we know that we should be able to converge faster or less fast in terms of n to some power, for example, when it should be easier to estimate smooth function than, for example, very complicated function. And so this is what we get here. So let me summarize the results we get. We see that here. So this is not complete. It's just for particular hypothesis we make. Here is the learning rate we get. So the first one is what we call polynomial decay kernels. So interestingly here, you see that we make an assumption on lambda I. And so lambda I was the sequence of lambda i's where the eigenvalues of the operator. So remember this, if you go back to the section on Mercer kernels, there were a few comments about the fact that, for example, if you have a polynomial decay, then it creates, so for example, for the uniform norm over the 0-1 interval, polynomial decay corresponds to an RKHS, which is a Sobolev space. And so in particular, the larger the S, the larger the degree of the Sobolev space, and therefore the smoother the function you have there, right? So in a sense, when you do polynomial decay kernels, there is some exponent here, which hides somewhere, for particular chairs of kernels, what is the class of functions you consider in your RKHS? Are they smooth or not? And so remember here that we have a super important assumption, which is that f star, so the true function that we estimate, should be in the RKHS and have a norm which is finite, which is ideally not too large. So there is an interplay here, right, between the choice of the kernel. In a sense, here we say that if you choose a kernel that describes a functional class, which, for example, describes a subordered space, and if f star is in a subordered space, then we prove formally that the MSE is bounded by the norm of f in the subordered space, which is a number, sigma square, which is just a parameter, multiplied by some rate, which is n to the power minus s over s plus 1. And so this is what we get. And something interesting, which I can say now, is that we can show that this is a good rate in a sense that if we did not do kernel regression, but if we did regression with any other method, that you could do regression with a random forest or with anything else, nearest neighbors, etc., then it's possible to show that you can never be better than this exponent, right? This is the theory of minimax estimation. So you can show that if you want to be good across the space of subordered functions of order S, then this is the best rate you can get. So this shows that not only did this shows that our analysis is quite sharp in the sense that we just have upper bounds, but the final upper bound we get is the best you can get. And the second thing is that kernel ridge regression is a good method in this case because it's one method that reaches what's called the minimax optimal rate for polynomial decaying kernels, and so corresponding f star. A couple more of results. If you assume that the lambda is decreased faster, so in a sense, decreasing faster means that the implicit dimension of the space, the complexity is smaller, then you get faster rates. You get log n over n. And if you assume that the eigenvalues are bounded, like they become 0 after some step, then you're really infinite dimension, and you can show that your MSE is proportional to the dimension over n, which is, so all these ones are minimax in the sense that we know that if you solve a regression problem in dimension j, then the best you can get in MSE is something proportional to the dimension over n. So this is, again, a minimax rate. Okay, so a couple of comments. I already did some of them. So the first comment is that, here I just showed the result over B tilde plus V tilde. As I said, we made this assumption that, some random matrix was fixed. As I said, in fact, it's just to help to make our life easier in this short video. But you can make the complete proof, and again, check the paper of Dicker, in particular, corollary 1 to 4. That shows slightly different upper bounds, but with the same rate, but without doing the simplification, the simplifying assumption. It's not a big comment. So I already said that the rates are good in the sense that they are minimax optimal. I already mentioned that in the case of subordered spaces, the speed n to the power minus s over s plus 1 is optimal. And if you want to know more, I encourage you to have a look at any reference, including the excellent book by Sasha Tsibakov on non-parametric regression. And finally, maybe a last comment is that I try to make a setting where everything is doable in just a few slides, but we could prove many more things. And in particular, something interesting that, if you're interested, you can read in the paper, is that kernel ridge regression is adaptive in a sense that even if you don't pick the exact, the best kernel, so if you assume that f is in a subordered space, but in fact it could be even smoother than that, then you can show that under some modeling, the same algorithm would converge faster if you make more assumptions on f star. And so in a sense, the rate is adapted to the complexity of the function f star, but this is well beyond the scope of this short lecture. All right, so something I did not say is how we prove that. Well, check the next few slides. Basically, to prove the bounds, we just used the previous lemma where we had some upper bound over the bias and the variance as a function of a j. And so the question now is, how do you pick J? In particular, depending on the assumption you make on the rate of decrease of the lambdas, what we will do here is that we will always pick a J such that a given lambda, so the lambda we choose is basically equal to lambda J. So this will give us this will give us an upper bound when there is no J anymore. It only depends on lambda, and then if we pick correctly lambda, we can prove that both the bias, so the bias will be of the correct order, and the variance as well. So it's just a question of picking the correct J and lambda, and there is no particular difficulty. I mean, you need to to do some upper bounds. Please, if you're interested, check the details. You can redo the computation, but besides the small sharp bounds you do, there is no difficulty. It's just correctly choosing J and lambda. Right, and so this is, for example, in the big O notation, this is what's hidden. In the variance, for example, you get sigma square, you get the n to the correct term, and then you have some extra term which in the theorem was hidden inside of the big O notation. But here we have the exact expression. Right, so this is for the polynomial. Basically the same for exponential. Details left as the exercise. And by the way, if you want to check, again, there are papers that do that, and the same for finite run kernels. All right, so I think that's all for today. In short, this is both, so this section today was both an illustration of a technical aspects. So thanks to the Mercer kernels, we have this isometry between L2 and H, and this is an illustration of why this isometry can be useful from a technical viewpoint. When you want to do the theory, you need to estimate L2 norms, and here we showed that to upper bound the L2 norms, which is the MSE, we express it in the RKHS using the isometry, in the case of Mercer kernel, and this allows us to derive all the upper bounds that finally give us optimal bounds, so we don't lose anything. And the second comment is that this shows that kernel-rich regression is a good method, at least in theory. It reaches all the best possible asymptotic rates you may hope for. And I encourage you, coming back to these results, to think of, get some intuition of the interplay between the choice of the kernel, the assumption on the nu. So remember that the rate of decrease of lambda depends on the kernel and on the measure nu. So this means that some kernels are well adapted to particular distributions nu. And also on the fact that once you have decided of a kernel for a particular nu that gives eigenvalues, the third assumption here is that f star should be in the RKHS, right? So basically, another way to say is that when you make regression, you make assumption on the regression function f star. So typically, by picking a kernel, you pick an RKHS. So this is the first strong assumption. Do you assume that f star is in a Sobolev space, or is it in a Gaussian RKHS, etc.? And from this RKHS choice, then there is an interplay with the distribution of x through the eigenvalues, and the eigenvalues lambdas will decide whether you're in a regime with polynomial decay or exponential decay kernels. All right, thank you for your attention, and see you next time.